Great. Thank you so much, Sergey, for that wonderful introduction. I feel like you actually gave my first few slides for me in your description, which was very fun. So thank you again for the invitation to come speak to you all. Today, we're going to be talking about lunar magnetism, which, as he alluded to, sheds some light into dynamo processes on larger scales. All right, next slide. So planetary dynamo magnetic fields are generated by advection of conductive fluid inside a planetary body. Most often the time in terrestrial planets, that conductive fluid is liquid metal within the cores of those planetary bodies. So if you can use either paleomagnetic measurements or spacecraft measurements to show that a body either currently generates or once generated a core dynamo magnetic field, it tells you a few things. It tells you that your planet early in its history underwent melting and differentiation into a metallic core and an overlying silicate mantle. And the second thing that it tells you is that there is some mechanism acting to sustain the advection inside the body. You can have multiple ways of doing this. The first one is simply purely thermal convection of the core over secular cooling of the planet. And so if you can study the evolution of the magnetic field that was produced by convection, it can tell you about the thermal evolution of the planetary interior. Once you cool down enough for an inner core to begin to crystallize inside your planet, that freezing of the inner core is going to preferentially solidify metallic iron, leaving light elements in the residual fluid, which contribute to chemical buoyancy, which can also help propel a dynamo's convection. And then the third thing is that you can have external factors that can mechanically perturb cores and core fluids, such as large impacts hitting planetary bodies that shake up the core and through librations of the body and stir the core. And you can also have precession, either between the differential precession, either between the core and the mantle, or even between the inner core and the outer core. So these types of mechanical perturbations may also be capable of producing dynamos. So if we take a walk across the inner solar system, we see that magnetic fields are actually a fairly common outcome of the planetary formation process. Mercury, Earth, and Mars, and even small bodies such as asteroids and early planetesimals have been shown either from spacecraft measurements or paleomagnetism to have generated dynamo magnetic fields in the past. And one thing that is interesting about the moon, which is the body that I'm going to talk about today, is that it falls into this intermediate size range between kind of a full-scale planet, something that's, several thousand kilometers across in diameter, and an asteroid, which is maybe a few hundred kilometers across at best. And both of these end-member size ranges can produce dynamos of varying longevities, but the moon is somewhat in the middle, so we're kind of interested in what can actually create magnetic fields on an intermediate type of body. It's a great natural laboratory for studying this. So some of the mysteries we're going to talk about the moon today are, did the moon produce an ancient dynamo magnetic field? And if it did, what was the intensity, the duration, and the power sources responsible for that field? And then there are some other implications for the volatile history of the moon. For example, if there was a magnetic field on the moon, how much, hydrogen could be implanted from the solar wind, or would some of the charged particles, from the solar wind be deflected around the moon by its magnetosphere? So there are a few different ways to study lunar magnetism. So the first way is to look at the remanent crustal magnetism that's preserved in the lunar crust via orbital measurements. The second approach is the one that I spend most of my time on, which is paleomagnetism, actually studying magnetic records that are preserved in individual lunar rocks. And then the third way is to do theoretical studies, either studying lunar mantle evolution or maybe eventually moving on to doing actual MHD simulations of, fluids in the lunar interior. And so I'm going to touch on each of these three styles of doing lunar magnetism today in various parts of the talk. So first, I'm going to begin with crustal magnetism. So ever since the Apollo era, the first spacecraft that were sent in lunar flybys actually did detect that there was no global magnetic field at the moon at present, but there was some kind of remnant magnetization in the crust. More recently, the Lunar Prospector and Kaguya spacecraft have made detailed magnetic maps of the moon. And so I'm showing you one of these magnetic maps right now. So what we are looking at is the lunar remanent crustal field. I believe this is the total field map in log scale that we're looking at right now. And on the left is the near side of the moon, the side that you're used to looking at in the night sky. And on the right is the far side of the moon. And the first takeaway is that actually much of the lunar crust has a very weak but non-zero magnetization preserved in it. So this is our first indicator that that moon has a magnetic history of some sort, and that the moon may have generated a magnetic field in its past. Now, if I switch from log scale to linear scale on the next slide, what we can also see is that there are areas of the moon which have like the strongest crustal magnetic anomalies, and the areas with the strongest magnetic anomalies are extremely localized. Some of them are isolated in kind of, random-ish looking places on the moon, but others are seeming to have some relationship with impact processes. Now, before I was showing the near side and the far side, what I'm going to show on this next slide is only the far side and looking at it sort of from near the south. So here's the South Pole for reference. And here on the left, we have magnetic field strength. And on the right side, we have a topography map. And so what we have seen is this slight pattern that some of the strongest magnetic anomalies on the moon may have some relationship to impact processes. The solid ellipse that we see here outlined, this big one, is a big impact basin called South Pole Aitken Basin. It is the largest impact basin on the moon. Near that, in the northwest rim of South Pole Aitken, there are a bunch of these very strong anomalies, but these locations of strong anomalies also coincide with the antipodes of other impact basins that were on the near side. So for example, the dotted lines here on the left is the antipode of Imbrium Basin, in the middle is the antipode of Serenitatis Basin, and on the right here is the antipode of Crisium, which is another large crater on the moon. So this led to another question of, what is the relationship between impacts and magnetism? Is it possible that these anomalies, are they recording a dynamo field, or could there be some kind of transient impact generated field that's produced? Here on this slide, I'm also going to show you, if we look at the near side of the moon again, here's Imbrium Basin. So it's kind of the largest crater that you see when you look up at the moon. And then there are magnetic anomalies that seem to line up radially coming from Imbrium Basin. Of course, that doesn't necessarily mean that they are sourced from Imbrium ejecta, but this is one of the hypotheses that maybe iron from the impactor was, ejected all over the moon. And we see these rays that are the sources of magnetic anomalies as well. So all in all, it just comes down to, are we recording a dynamo field, or is this the result of some kind of transient impact field produced by plasma? Whenever an impact hits rocks in the crust, kind of vaporizes them, and then you have these moving conductive plasmas going around the moon. So one way to try to differentiate this is to try to see, whenever you look at impact basin melt sheets, where are the magnetic anomalies inside impact basins actually located? And so here's a study by Oliveira et al. 2017, and they looked at a variety of old impact basins on the moon. And so here's Humboldtianum, Nectarius, Crisium, and Serenitatis. And whenever you look at this figure, the way that these are organized is you have the outer rim of the basin, and then you have the peak ring, and then you have the inner melt pool, basically. And so what we end up seeing is that the magnetic anomalies inside basins are either inside the central melt pool, or they're outside the peak ring. in what's called the annular trough, which is another area filled with melt, basically. So what this tells us is that the anomalies are located either centrally in the melt or in an outer annular trough of melt. And melt sheets cool to the Curie temperature of iron, which is 780 degrees Celsius, very slowly. And modeling of impact melt sheet cooling tells us that it can take over 100,000 years for a melt sheet of 5 to 10 kilometers thickness to actually cool below the Curie temperature in order to record a magnetic remanence. And so the idea is that you must be recording a dynamo field, because a dynamo field may be stable over such long time scales, whereas models and theoretical calculations have suggested that a transient impact generated field would last something like 1 day in duration. And that short duration precludes or rules out recording a large scale magnetic anomaly in an impact melt sheet. So there's some evidence that at least, going into the Imbrian period, maybe up to about 3.7 billion years ago, lunar impact basins are magnetized. Not all of them, but many of them. All right, another thing that people do with lunar crustal magnetic data is they try to find isolated magnetic anomalies and use an inverse method called Parker's method to establish the magnetization direction that is recorded in the anomaly. And the way that this works is that you pick a magnetic anomaly and you assign a grid of dipoles to different locations inside that anomaly. And each dipole is assigned the same direction, but the intensity of each dipole is spatially varied. And then you just run this over and over with many different directions applied until you find which direction and dipole intensities have the lowest misfit. And that's the way that people determine the magnetization direction inside an anomaly. And then they can convert that magnetic direction to what the paleopole location would be for a lunar selenocentric axial dipole field. And this is intended to try to get some constraints on what the geometry of the ancient lunar field would have been. And there have been many studies that have used similar methods to get paleopole locations on the moon, as summarized here in this review paper with Zoric et al., which is in press. And what we find is that actually these paleopoles people are getting are all over the place. And this is a little bit confusing because we are not sure if the problem is that the lunar field is not dipolar. It seems like the moon has a pretty small core relative to its overall radius, and higher order fields would fall off more quickly from the core. So you might expect a field to be more dipolar, but that's not necessarily what we're seeing in the crustal magnetic data if these inversions are correct. The alternative is that you could have a dipolar field that is not axial. It's a dipole field that's moving around. That has been hypothesized by several authors. Or, another possibility is maybe there's some issue with the inverse methods, which assume that one anomaly is unidirectionally magnetized, and maybe there are some complexities that are leading to erroneous paleopole determinations. But that is pretty much what we can glean from crustal magnetism. So what we've learned from crustal mag is that the interiors of many early impact basins do contain magnetic anomalies, which are indicative of at least some kind of intermittent dynamo operating from the pre-Nectarian, which is, about 4.5-ish, close to that billion years ago, all the way into the Imbrian period. I wanted to clarify, actually, the South Pole Aitken Basin, which is the oldest impact basin on the moon, is not definitively dated. So we think maybe it's around 4.35 billion years old, but we're not sure. Anyways, but we have some magnetic history recorded in basins going into the Imbrian. So now we're going to start talking about paleomagnetism, which is what I work on. We can get additional constraints on the history of lunar magnetic fields from actually studying lunar samples. So this is me holding an Apollo 15 Mare basalt back actually when I was in grad school, but this is my favorite picture of me holding a moon rock, so I keep it here anyway. And what we do is we measure them inside a paleomagnetism laboratory. And this is a nice digital rendering of my lab at Stanford that was designed by one of my PhD students. So I totally suggest that you check out this website if you get a chance. If you go onto the website, you can actually click on different instrumentation in the lab and it'll tell you what it is. And there's like even like little animations of how things move around. But basically, what we do is we take moon rocks and we measure them inside a superconducting rock magnetometer. That magnetometer can measure the intensity of the magnetic field preserved in this magnetization preserved in the sample along the X, Y, and Z axes. And then we can get the resultant vector of magnetization, intensity, and direction in rocks. And we can study those rocks' magnetizations in order to infer the history of planetary magnetic fields. So before I get into that, I'm going to give you a little bit of a primer on how rocks actually acquire magnetization. If you have an igneous rock or an impact melt rock, which are the two primary types of rocks on the moon, they will acquire a thermoremanent magnetization when they form. So if you have a rock that starts out really hot, it will crystallize magnetic grains. In the case of the moon, it's metallic iron or iron nickel alloys. And if there's a field present at the time that the rock is cooling, the rock will record a essentially permanent magnetization that is biased in the direction of the ambient field at the time the rock formed. And that is recorded as a magnetization. If the field is weaker, this biasing process becomes less efficient. So maybe only, some grains are magnetized in the field direction and other grains are randomly oriented. So you have a net weaker magnetization. And if there's no field around, there's nothing to bias the magnetization directions within grains. So you would have a net magnetization of 0. The takeaway here in paleomagnetism is that the magnetization direction is oriented towards the ambient field direction, and conveniently, the intensity of the magnetization is directly proportional to the strength of the ambient magnetic field. So during the Apollo era, paleomagnetists measured the remnant magnetization in numerous Apollo samples, which is what we're showing on this plot here. And these samples had different ages. And they tried to determine what was the paleointensity or the strength of the ancient magnetic field preserved in the rocks. I'll get into how we do that later. But the takeaway is they found these patterns that between about 4 and 3.5 billion years ago, there was a wide scatter in inferred paleointensities, and many rocks seemed to have intensities that were similar to what the Earth's magnetic field strength is today. After 3.5 billion years ago, there seemed to be some kind of drop off, but also like weirdly non-zero numbers going up to nearly the present. And so this Apollo paleointensity record was very tricky to interpret, and we weren't sure if it was right, and we weren't sure what it meant. There were some uncertainties. We had no data really before 4 billion years ago because we just didn't have rocks that were the right age to study. Lunar thermal evolution models, given the small size of the moon and the exceptionally small size of the core, we think it's less than 400 kilometers in radius compared to the moon's 1,700 or so kilometers in radius. The cooling of the moon would seem to hint that you might not be able to sustain thermal convection past 4 or 3.5 billion years ago. So how do we have non-zero paleointensities later in lunar history? And then there are also dynamo scaling laws that are based on kind of observations of stellar dynamos or other planetary dynamos and models. And what they predict is that the moon should not be able to generate a convective dynamo field that's greater than even 1 microtesla a lot of the time. If we want to be really generous with the parameters, you can't make a field more than 20 microtesla with purely convection. So all of this was confusing with respect to the lunar paleomagnetic record. So what we've been doing in the last few years is we've actually been going back and remeasuring Apollo samples and trying to figure out, using modern methods, what was the real paleointensity history of the moon? And also, are these magnetic records even from the moon? So I'm going to walk you through one of my recent relatively recent studies, as well as another super recent study during the rest of this talk. And so in 2017, I published a paper which studied this Apollo 15 Regolith Breccia. So what this breccia consists of is basalt clasts that are basically welded together with impact melt. And the impact melt formed at the time of the impacts that solidified the breccia, which ended up being about 1.4 billion years ago. We took 12 glassy matrix subsamples from the interior of that breccia. We cut off the clasts. We only used the clasts to help orient the pieces with respect to each other because they were recognizable features. And we conducted paleomag experiments on that glass. All right, so we do two types of demagnetization experiments on this rock. The first type is a room temperature experiment called alternating field demagnetization, where we progressively expose our rocks to alternating magnetic fields that basically go up, down, up, down, up, down with decreasing amplitude. And we measure the remnant magnetization left in the rock after each alternating field step. And then after we measure it, we increase the intensity of the field, measure it again, increase the intensity of the field, measure it again, until we've removed all the magnetism in the sample. Likewise, in a parallel set of experiments, we heated the rock progressively from room temperature up to the Curie temperature of iron. So from 25 C to 780 C, again, progressively removing the magnetization from the rock. So the question is, why do we do this? Well, let's walk through an actual experiment to show why we do this. The natural remnant magnetization inside a rock, the NRM, is the resultant sum of all magnetization vectors preserved in a sample. You might have multiple magnetizing events that affect the history of the rock. Whenever a rock initially forms, that will magnetize all the, most of the grains in the rock, basically, and bias it in the field direction. So what's going to happen is that you're going to have a very strong, like relatively tough remnants to remove. That is the original remnant magnetization in the rock. But later, a secondary event like a shock event, or maybe exposing the sample to a magnet or something like that may imprint a secondary contamination magnetization, which is the blue vectors here on these grains. So these secondary contaminations are usually pretty easy to remove, so they come off pretty quickly. So let's look at the total vector, the NRM. That's what we have in the rock before we do anything to it. And then we're going to apply an alternating magnetic field, a low one, and we're going to randomize the weak grains that contain an overprint. And we're going to keep randomizing those weak grains until they've been totally randomized. And then whatever is left, which is the original magnetization in a rock, is going to have an origin trending vector that persists to very high fields. And that's what we're trying to look for if we're trying to establish that this is a remnant magnetization that is lunar in origin. We want to see that origin trending vector. The next thing that we do once we have isolated a magnetization direction is we want to understand what was the strength of the magnetic fields that created that magnetization. So what we do is we conduct a paleointensity experiment. We're using room temperature methods. We use alternating field demagnetization at increasing steps to totally remove the magnetization from a rock. Then we apply another artificial laboratory remanence into the rock in order to simulate a thermal remnant magnetization. And then we demagnetize that as well using alternating fields. So we compare the rate that the NRM is lost to the rate that the secondary magnetization that we've applied in the lab is lost. And then the slope of that line, which is the delta NRM over delta, in this case, saturation isothermal remnant magnetization, the slope of that line times some calibration factor, which is experimentally determined, gives you the strength of the paleofield. And these room temperature methods are accurate to about a factor of 2 or so, maybe factor 2 or 3 in accuracy. If we were to do a canonical heating experiment, the way most people study Earth rocks, we would heat the sample to the Curie temperature slowly, but in between heating steps with zero field, we would actually heat the sample again to the same temperature in the presence of a field to impart it with partial thermoremnant magnetization. So this is a little bit complicated to explain in 1 minute, but the general takeaway is, again, the slope of the line of how much natural remanence is left in the sample at each temperature step versus how much laboratory magnetization is gained in the sample at each temperature step The slope of that line times the strength of the lab field that you apply gives you the strength of the ancient Paleofield. So this is in a nutshell how we do these experiments. So in the case of my sample, we demagnetized 12 subsamples that were mutually oriented with respect to each other. We found that their magnetization directions were relatively uniform. They were very well clustered. The magnetization persisted to very high temperatures, almost the Curie temperature of the sample. And whenever we did a thermal paleointensity study of that origin trending component, which I'm showing in green here, we got a paleointensity of about 5 microtesla recorded in this rock. And this actually passed quality criteria tests that are commonly applied to terrestrial studies as well. So using these methods and similar methods, modern studies have compiled what is a new paleointensity timeline for the moon. And so we have evidence that there were actually Earth strength-ish magnetic fields, at least sometimes during early lunar history till about 3.5 billion years ago. Then we have a bunch of samples that are shown in red here that are not magnetized. But what are these points? These points are upper limits on what the field strength could have been for those rocks to not show any magnetic signal. So it turns out that most moon rocks are actually pretty bad magnetic recorders. And so just because we don't see a remanence doesn't mean the field wasn't there. I mean, it could mean the field wasn't there, but it could also mean that there was a weak field and it just didn't get recorded. So then we have this one point that's a bit younger, about 1.5 billion years ago, where we have a non-zero remanence. And then we have some other very young rocks that ended up being exceptionally good magnetic recorders, very fine magnetic grains and impact melt rocks. And it turns out that those rocks were not magnetized at all. And that pins the field strength about 1 billion years ago and less to basically 0. So the takeaway is that there was at least an intermittently strong early field. The field probably declined by a factor of 10 in intensity. There may have been a weak late field, and then the lunar dynamo definitely ceased, we think, by around 1 billion years ago. So people have been using this chronology to try to infer what dynamo mechanisms may have been occurring on the moon at different points in time. And another thing I want to touch on right now before I move on is that these early measurements are largely based on Mare basalts, and these later measurements are largely focused on impact glasses. And I'll come back to why this is significant later in the talk. But in the meantime, people have used this paleomagnetic records to try to come up with different dynamo mechanisms that could have operated at different times in lunar history. And as I mentioned at the beginning of the talk, it's very difficult to have a long-lived lunar field with purely thermal convection. This tends to peter out around 3.5 billion years ago at maximum. Others have proposed that you could have thermocompositional convection powered by inner core crystallization, and those fields could potentially last for much longer, even up to 1 billion years ago or something like that. And so that might be consistent with a weak field for much of lunar history. Then there are other authors that have proposed that precession, either between the differential rotation, either between the core and the mantle, or the inner core and the outer core, could produce a longer lived dynamo. And then there's another mechanism written by Labars et al. 2011 that you could have giant basin forming impacts, shake up the mantle, cause the moon to librate, and while it's recovering from that impact, and those librations can produce transient dynamos that last for a few thousand years after each impact. So all in all, there have been a lot of different hypotheses proposed. There's even been proposed this idea that the moon has a partial melt layer that's overlying its core based on seismic data, and maybe there was a basal magma ocean dynamo operating within the moon. The only problem with that one is we're not sure if the basal magma ocean could be conductive enough to actually do this in reality. However, all of these mechanisms, for the most part, suffer from the same kind of lunar core energy dilemma. And that is that based on dynamo scaling laws, the moon should not be able to produce very strong fields. So this Christensen scaling law was applied to many of these different dynamo models to predict what the field intensities produced by those models would be. And this is a complicated equation, but really only a couple terms are changeable. So a couple terms matter. The first one is that, okay, the most important one is that you need to have enough super adiabatic heat flux coming out of the core. And that is this Q sub A term. And the reason it's hard to produce a strong lunar magnetic field is that the field intensity depends on Q sub A to the 1/3 power. That means you have to cube Q sub A in order to see any appreciable change in possible field intensity. And so really right now, only a few mechanisms can produce fields that are several tens of microtesla. One might be the precession dynamo, or a basal magma ocean dynamo, or some kind of intermittent dynamo that can have longer, higher field intensities every once in a while. So this lunar core energy dilemma probably led to some skepticism in the lunar paleomagnetic data. So recently there was this other paleomag paper that came out last year by Tarduno et al., which was called Absence of a Long-Lived Lunar Paleomagnetosphere. And what this paper did was they measured a number of Apollo samples with different ages. And they didn't measure bulk samples in this case. They actually took out like single crystals from within the samples and used a magnetometer with high sensitivity to try to measure the magnetic intensity in those individual crystals. And their takeaway was that they didn't think that those crystals held a substantial magnetization. So they were arguing that there was not a lunar dynamo on the moon. Actually, what they found was that these crystals had upper limits of like 1 to 2 microtesla on the field based on the experiment that they were doing. So what we're going to show is a figure from their paper. And so here are some of the previously published modern paleointensity values. And then here they superimpose in the blue their samples, which they plotted at 0. Even though it's not necessarily totally 0. And they are arguing that there was no dynamo at all. So from our perspective, it was a little bit strange that they didn't see any of their samples that did have a positive magnetic signal. But at the same time, you can see that there are some differences between the samples that did have signals and the samples that didn't necessarily have signals. So one is that a lot of their samples did not match ages with this high field epoch that was inferred by other studies. They have one rock that's actually a very complicated rock that's about 3.9 billion years old. So it's sort of earlier than the high field epoch inferred from other Mare basalts. And then these samples, Apollo 12 and Apollo 15, I personally have never seen a magnetic record in an Apollo 12 or Apollo 15 basalt, really. So the fact that they didn't see anything in these younger rocks doesn't necessarily surprise me. Maybe there was no dynamo at that time, and maybe some of this is evidence that the dynamo was intermittent. So that doesn't necessarily surprise me. One thing that was odd is that they found this one impact glass-coated rock, 64455, that was 2 million years old, and they did find some magnetization in that rock, which was also confusing because in our studies, we have not found magnetization in impact melts that are that young. So that was also weird. One thing we did find out from doing some forensics is that this sample was actually a returned sample that they studied, which meant that NASA had allocated it to someone else to do a different type of experiment. And then that sample was returned to NASA. And then they took that chip and did paleomag on it. So we're investigating the possibility that maybe there was some kind of magnetic contamination associated with that sample. So, there needs to be a reproducibility study done on that young sample to see if that is really evidence that if that sample is contaminated, what does that mean for earlier samples? So this is really an ongoing kind of issue that we'll be working on for the next few years. One thing I will say for this paper is that it doesn't actually explain why some of these earlier Mare basalts are magnetized. There is no compelling explanation for that in that current paper. So I'm going to go through my next bit of talk to talk to you about why I still think there was at least an intermittent dynamo operating on the moon. All right. So the key question is, these earlier Mare basalt samples that do appear to be magnetized and have higher paleointensities, are these actual dynamo records? In order to show that they are, we have to rule out some other things. So the first thing we need to do is we need to rule out the possibility that these samples acquired a shock magnetization in an impact plasma field on the moon. And this can happen because let's say you have a rock with some pre-existing remanents or even no pre-existing remanents. If you have an impact occur and you're exposing that rock to shock pressures, that pressure can actually overwhelm the magnetization initially recorded in grains and impart a new magnetization in whatever field is present at the time that the shock wave passes through. And that could be a transient impact field. And as a result, a rock might have a secondary contamination, from a impact field from shock remanents. So we have to kind of rule that out. Another thing that we need to rule out are terrestrial magnetic contamination. This could be from fields on the Apollo spacecraft or magnetic tools. This can be from cutting the rocks dry at NASA whenever they were preparing the samples back in the 70s. They didn't want to get them wet because they didn't want to contaminate them, so they just dry cut them with a bandsaw or circular saw, and that can cause frictional heating of the sample. One thing I can verify is that actually none of our Mare basalt samples from either the MIT group or my group were actually from saw cut faces, so we can rule out that one immediately for our samples. Another possibility is that exposing rocks to the Earth's magnetic field for a long time can partially remagnetize them as well through a process called viscous remnant magnetization. I can also say that our earlier studies have done experiments where we actually measure how rocks acquire viscous remnant magnetization, and we show that that cannot substantially contribute to the remanents in those rocks as well. So we should consider most of these boxes checked in terms of ruling them out as a source of remanents. So what we need to do is, if we're going to study Mare basalts, these rocks between about 3.9 to 3.5 billion years ago, we need to choose our samples carefully. All Mare basalts are good samples from the perspective of ruling out thermal remanent magnetization from impact fields, because they are all slowly cooled relative to the duration of transient impact fields. For the largest basin-forming impacts, those fields last for about 1 day. For smaller impacts, those fields may last like seconds to minutes max. And so if a rock is really cooling from above the Curie temperature of basalt, it's going to take hours to days to cool to the Curie temperature. So we're not going to record that as a thermal remnant magnetization. Next step is that nearly all Mare basalts lack petrographic evidence of shock. They don't have shock deformation features in them at all, for the most part, which limits their peak pressures to about less than 5 gigapascals. So what my grad student at Stanford is doing right now, sort of as a follow-up to this Tarduno paper, and it's, calling out of the lunar magnetic record, is we are looking at these 4 Mare basalts very carefully. And so we chose these 4 samples, and we did really detailed shock petrography. And what we found is that only one of the samples showed any petrographic evidence of shock. In this case, we had some undulatory extinction in olivine, which showed that it was shocked to at least 12 gigapascals or so, something along that lines. In terms of ruling out terrestrial contamination, none of these samples were saw cut. We also conducted experiments to see how they responded to the Earth's magnetic field, and they did not respond in a way that was strong enough for them to actually have recorded much of remanents from the Earth's field. Before we even demagnetized the samples, by the way, we also stored the stored the samples in zero field in a magnetically shielded room for months. So whatever terrestrial contamination might have been acquired should have decayed away by then, because it's actually kind of a logarithmic process where most of the change happens right at the beginning, and then it levels off after even just a few hours. And then we also studied the rock magnetic properties of these samples to see what kinds of magnetic recorders were inside them. So we do this in two ways. We first did imaging of the samples using SEM and EDS, and also even microprobe measurements to get the compositions of the magnetic carriers. What we found is that the magnetic carriers in these samples are tiny grains of iron, nickel, or actually more purely iron in most cases, without very much nickel, that are inside a iron sulfide mineral called troilite. Troilite is not magnetic. It's anti-ferromagnetic, which means that its spins cancel out, so it doesn't record a remanence. But we do have these fine-grained iron nickel grains inside there. And I'm not going to get into the details of what the plot on the right means. It's a first-order reversal curve plot. And what it tells you is that there's two populations of magnetic grains in the sample. There are some large isolated iron grains, which produce this signal that we see here. Those are poor recorders, but there are also these smaller good magnetic grains, which are good recorders, that produce this central ridge along this plot. So nevertheless, we have iron nickel of different sizes. That's being the magnetic recorder. So out of the samples that we did measure, 3 of the samples, 10003, 10069, and 10071, actually do show that there are magnetizations recorded inside the samples. And so these paleomag plots are very tricky to interpret. But what we're doing here is each dot is the endpoint of the magnetization vector after an individual demagnetization step. The magnetization vector is a 3-dimensional vector that we are projecting into a 2D plane. So we're taking all the points from the vertical plane, and we're showing them in white, and all of the magnetization vectors from the horizontal plane, that component, the horizontal component, are shown using black. Okay. So the easiest way to read this plot is to just choose one color, either choose white or choose black, and see how the trends go. So in this case, let's look at this bottom plot. I'm going to choose the white points, the northeast plane projection. And I'm going to say that there's some overprint component that is removed at a low field strength. You keep demagnetizing to about 12 millitesla. You remove another overprint component, and then you have an origin trending vector that looks pretty nice and persists to very high fields. Same thing with these other samples. There are some overprints, but then we have an origin trending vector. Here's another overprint, and then we have an origin trending vector. This data for the sample is less clean, but there is some high coercivity or high field remanence in this one as well. Interestingly, the one sample that did not have a stable magnetization is actually the rock that we found was shocked. 10044. Its magnetization was very noisy. We couldn't isolate any magnetic components in that one. So we're not sure if that's because of shock demagnetization, like maybe the shock event was after the dynamo died and there was no impact field recorded, or maybe this rock has poor magnetic recording properties or something like that. We're not quite sure why this one doesn't look magnetized, or maybe there was no field at the time that rock formed. What we did was we measured multiple mutually oriented subsamples from each rock. So each rock has a different color on this plot. So here in the red are the points from 10003. On the yellow, this is the sample that we didn't have any stable remanence, hence our error ellipses on directions are very large. All the pieces from the blue, 10071, are similar in direction, and all the ones in green from 10069 are similar in direction. So each of the 3 rocks that are magnetized are uniformly magnetized. So that's another indicator that we're recording a stable remanence from probably a lunar field. Just to be extra sure, we wanted to rule out the possibility that these rocks are recording fields from the spacecraft. So samples were actually exposed to fields 2 to 5 millitesla, or 20 to 50 Gauss, if you think in CGS units, on the spacecraft. So what we wanted to do was simulate this experience in the lab and see what does that contamination actually look like in these lunar samples. And so what we did was we got a neodymium magnet, we taped it to the inside of a jar, basically. Sorry, I realized I'm freezing a little bit. We taped a neodymium magnet to the inside of a jar, and we actually used a Gauss meter to figure out how strong the magnetic field was at different points along the dipole axis of that neodymium magnet. And then we exposed our samples to 50 Gauss or 5 millitesla for 24 to 48 hours. And then we immediately took them inside the lab and started demagnetizing them to see at what point that contamination from the lab magnet would be removed. And what we found was that the contamination was always removed by about 10 to at maximum 20 millitesla, which meant that the highest coercivity grains inside the rock, the most stable magnetic recorders, were not affected by that magnet at all. And so just to show you a recap of what our natural samples magnetization looked like, we had magnetism persisting up to 100 millitesla, whereas any hand magnet contamination was removed by about 15 millitesla, which is actually similar to the fields that our secondary remanences were removed at in the real sample. So what this tells us is that this is not a spacecraft field. Another thing that we wanted to investigate was, are these remanences in the rocks, the true remanences, shock remnant magnetizations from impact plasma fields? We say this is unlikely. First of all, there's not a whole lot of evidence for strong shocks in these samples. The other thing is that on other lunar samples, we have done, from the same lithology, Apollo 11 Mare basalts, we have done pressure remnant magnetization acquisition experiments to see how the behavior of a shock remanence looks compared to the natural remanence of a lunar sample. And what we have always found is that if you look at the normalized moment remaining in a sample compared to the alternating field step that we use to demagnetize the sample, the shock remnant magnetization here applied at 1.8 gigapascals was always much weaker and was always removed much more easily than the natural remnant magnetization in the red in Mare basalts. So we've done this in all of our previous studies, basically, and shown that the natural remanence does not resemble a shock remanence in character. The other thing to keep in mind is that pressure remanence or shock remanence is a weaker form of remanence than a thermal remnant magnetization. If you give the sample a thermal magnetization and a shock magnetization in the same field intensity as each other, the shock remanence is only going to be 1% of the intensity of a thermal remanence, or 10 to the negative 2 for moon rocks. So in this case, we did this experiment on some other Apollo basalts and found that shock is 1% the intensity of TRM. So you would need really strong fields from impacts in order to produce a similar looking NRM intensity. And even if you did have a similar NRM intensity, the character of the demagnetization would look different. So based on this, here's a compilation of all lunar paleomagnetic data acquired to date that my student put together. And so the gray circles are the Apollo era paleointensity values. So you can see there's a lot of scatter. The other modern paleointensity measurements are shown in red. And then where we have a positive result, if you have samples with a negative result where you don't see anything, those upper limits are shown in white. So you can see some upper limits. We're including the Tarduno samples on this plot as well. And then here's this study that my student is doing. We've studied a few more Mare basalts and gotten paleointensities that not only just replicate some of the higher field measurements that we saw earlier, but also we even had one sample that had a stable remanence from a weak field, something like around 4 microtesla, which is actually cool because we're showing that there was some fluctuation, order of magnitude fluctuation in field intensity, even during the high field epoch on the moon, which is pretty cool. So maybe some of what we're seeing is just natural fluctuations in the lunar field intensity and not necessarily the result of a dynamo being off all the time or whatever. Okay, and field fluctuations should not be unexpected. I just want to give a comparison. On the left, this is the Earth's virtual axial dipole moment in the last 400 million years. And what we found is that the Earth's magnetic field fluctuates even within the last 400 million years by a factor of about 15. And if we filter the lunar data, so the colors are filtered data, and the red ones are the highest quality data, blue are like acceptable on the Earth. If we use a similar filtering technique to filter lunar data, what we find is that the moon's paleointensity fluctuations are probably about a factor of 23, which is actually not that different from the Earth's changes, which are about a factor of 15. So then we got to circle back. Well, what is the dynamo mechanism? We cannot still really overcome this problem of these dynamo field scaling laws not being able to produce very strong magnetic fields that are sustained on the moon for a long time. Most of these parameters are fixed. The one thing we really need to change is the super adiabatic power at the core mantle boundary. And so one way, this is a recent modeling paper that I wrote with my collaborator, Alex Evans, and we tried to come up with like an alternative dynamo mechanism that could produce an intermittently intense dynamo. And so what we invoke is this concept of cold diapirs that sink to the core mantle boundary, and that could trigger more vigorous core convection. And I'll get to the uncertainties associated with this at the end. I'm just going to talk about this really fast in the last few minutes. How do we do this in reality? We're going to invoke a process that occurred during lunar magma ocean solidification, right at the beginning of the history of the moon. And what ended up happening is the moon formed a magma ocean. It was initially molten. And whenever you have the crossing of the solidus and the adiabat, that's what causes the magma ocean to start to solidify. And in the case of the moon, it started solidifying somewhere in the middle, and you began to crystallize out olivine and pyroxene and other mafic minerals, and they started to sink and started to solidify the moon from the bottom up after they sank. And then later in the middle, again, you started to crystallize not only olivine and pyroxene, but also anorthite. And that anorthite was buoyant, it was very light, and it floated up to the top of the moon and formed this white anorthositic crust that we see on the moon today. And what ends up happening is in between the anorthite layer and the more mafic materials, we had this layer of incompatible stuff called creep, or rare earth elements and phosphorus, that forms between the lunar crust and the lunar mantle. And what we have is this layer not just contains, creepy stuff, it also contains ilmenite in the very, very residual urcrete. And so ilmenite is actually negatively buoyant compared to the stuff that's underneath it. Actually, it's more dense. So what's going to happen is over time, that layer might founder in diapirs that sink to the core mantle boundary, and those blobs might actually be colder than the core. So if those blobs encounter the core mantle boundary, they may actually cause some localized cooling of the core and could trigger like more rapid convection. And so in the Stokes regime, a 60-kilometer blob diapir can reach the core mantle boundary within a few 100 million years. There are some thermal models that show that that diapir should not totally thermally equilibrate with the mantle on that time scale. And there are also some other models of lunar internal evolution that suggest that these diapirs could continue to sink to the core mantle boundary till about 3.5 billion years ago, depending on the lunar mantle temperature and viscosity. And that's a period that might be coincident with this high field epoch that is producing intermittently high paleointensities on the moon up till that time. What we found is if we just use that Christensen scaling law, we can actually produce surface fields of around, up to, 50 microtesla or more that persist for several 100,000 years after each diapir encounters the core mantle boundary. So there is a possibility that you could have intermittently enhanced dynamos that have stronger fields from time to time. And that might actually be consistent with some of the Apollo magnetic records and even modern paleomagnetic records that are showing that some samples seem to record dynamo fields and other samples do not. And so that would be a very interesting result. I'm going to caveat by saying that, a parallel process on the Earth is when you have the sinking of a subducting slab and the cold slab hits the lunar core and actually causes a lot of changes in the Earth's magnetic field. We think there might actually be a triggering of magnetic reversals, which might actually look like a lower paleointensity. Something like that is also possible on the moon, but there's no MHD models to tell us which way things are going to go on the moon. So I think there's a lot of future work to be done in core field modeling on the moon that I would love to have someone take this and run with. So in conclusion, what we have is we have positive magnetic records in Mare basalts in present and past studies, and we think that they likely reflect a dynamo field rather than contamination by impact fields, the Earth's fields, spacecraft fields, or sample handling. This dynamo looks like it might actually be intermittent, both based on the crustal magnetic record of some basins being magnetized and others not, as well as some of these Apollo sample studies. I don't think that our work is necessarily incongruous with the more recent work by Tarduno et al. It's possible that both of these interpretations are correct. The high field epoch between 3.9 and 3.5 billion years ago might have been not so high all the time, but it might have instead been marked by high paleointensity variability, even for a dynamo that's still active. And then 4, basin forming impacts mechanically stirring the lunar core, or maybe foundering of cold titanium-rich cumulates left over from magma-ocean solidification may have episodically enhanced the ancient lunar dynamo field. So I guess I'm kind of walking towards this idea that the lunar field could have been intermittent or at least intermittently intense. And there's a lot more work for modelers to run with these ideas and see how feasible they actually are. And I'm very excited to see how added sample studies and added modeling studies are going to evolve in the next few years. Thank you so much, and I'm happy to take questions.